Now this video is on model-free daily P volatility. So I introduce you to the Corsi 2009 method that gives a framework to estimate in a model-free way expected next day's volatility as a function of realized returns only. Now the method is simple, you just need OLS. In order to understand the concept, you need a little bit of stochastic calculus just to understand the basic notation. Which means in that video, I assume you already have a basic understanding of stochastic calculus. If not, then take that video here as a motivation of why you need a basic understanding of stochastic calculus, even though you simply want a vol forecast. So let's start. Now, Corsi makes the simplifying assumption that price changes are not affected by discontinuous moves. Now that says that prices cannot jump, but do rather diffuse continuously. Now that assumption can later be relaxed, yet for this video here I like to keep it simple and intuitive. So let PT be the log price at time t of an asset. So we now assume that the instantaneous change of that log price from its conditional expectation follows a diffusion. That means the following equation holds, where dpt over dt, being the instantaneous change of the log price per time unit, minus its conditional expectation, is simply the conditional volatility sigma t times a Brownian diffusion, dwt over dt. Now, for the moment, you just need to visualize the dwt over dt as a random variable that has a Gaussian distribution with mean 0 and variance 1. As a footnote, of course, strictly speaking, in the math sense, dwt over dt is not defined, because a Brownian motion is not differentiable. But dwt is well defined. But for now, I don't want to get into the geeky yet important details of stochastic calculus. For this video, I assume you have a basic understanding of that stochastic calculus notation. And I try to provide explanation with as little stochastic calculus as necessary. Now, nevertheless, you might still see the need to get a basic understanding of stochastic calculus. And in that sense, this video on the model-free vol forecasting provides you also with a motivation of why stochastic calculus is necessary. So let's get back. Let's consider the time interval t minus 1 day up to t, which is one trading day. So the full trading day is represented here by the time interval 1d, where d stands for day. Now, the integrated daily variance, denoted as IVD is defined as follows. You simply take the integral of sigma s squared ds from s going from t minus 1 day up to t. Now, if you want the integrated daily volatility, you simply take the square root of that last expression. Now, notice here, a series of seminal research papers have shown that the integrated daily variance can be approximated to an arbitrary precision through the sum of intraday squared returns. So ignoring the arbitrary small approximation error, I want you to take away that the realized volatility of a day equals that next expression here, where capital M is the number of evenly distributed sampling periods per day, which makes delta be equivalent to 1 day divided by M, and that's this intraday sampling period. So the square differences, which we add up, here the p of t minus j delta minus p of t minus j plus 1 delta to the power of 2, these are just the squared, continuously compounded returns within an evenly spaced daily subperiod. So in relation to my previous videos on gauge modeling and stochastic volatility models, it appears important to know that Anderson, Boleslev, Diebold and Labis 2003 in an Econometrica publication find that time series modeling of realized volatility shows superior out-of-sample forecasting ability relative to gauge and stochastic volatility models. So realized vol is the way to go if you want the best vol forecast. So far, so good. Now let's continue with the methodology. I also introduce the average realized volatility over the past week and the past month, which I denote here as RVW, for W being 1 week, and RVM, M standing for monthly. They follow the respective formula here. Now, as you look at these formulas, you note that both averages are simply an equal weighted average of daily realized volatility. So the weekly measure assumes 5 trading days per week, while the monthly measure assumes 22 trading days per month. Note, for empirical work, I recommend you annualize each return and volatility quantity to simplify interpretations and comparisons. So that 2009 Journal of Financial Econometrics publication of Professor Corsi used the above-mentioned concepts to introduce the so-called HRRV model. Now that stands for Heterogeneous Autoregressive Model for Realized Volatility. That model assumes that next day's realized volatility is an affine function in today's, last week's and last month's realized volatility. So mathematically, Corsi in 2009 writes that as tomorrow's realized daily vol equals the following expression: a constant plus beta d times realized daily vol at the previous day plus beta w times the realized vol of the previous week plus beta m times the realized vol of the previous month plus an epsilon error. Now I assume here for simplicity that the epsilon has an IID distribution with mean 0 and variance sigma square. Under that assumption, you can estimate the 4 plus 1 parameters of the model by OLS. Now, moreover, let's look at that last equation more carefully. If you do so, you might notice that this forecasting model looks like a constrained AR22 model for realized volatility. The constraints make you estimate only 3 slope coefficients, 1 intercept, and the error variance. In that sense, it's clear that you could extend that logic as follows. Instead of a scalar AR setting, you could also work with a vectorized AR model. That makes sense if there is empirical and ideally also theoretical evidence that other variables help to predict realized volatility. If that was the case, you simply add all variables into a vector and apply a constraint var22, simply following that logic from the last equation. And that exactly is what follow-up work has been doing. But it all boils down to that simple Corsi 2009 methodology, which is working really well in practice. So that HRRV model for the daily realized volatility works with a simple autoregressive structure. The new thing at the time was that it considers as explanatory variables realized volatility over different time intervals, going from daily to weekly and to monthly. Now, as for the underlying economic rationale, Corsi 2009 argues that investors with different time horizons react to different news and hence create different components of the frequency spectrum of volatility. Moreover, empirical evidence suggests that lower frequency volatility affects upcoming short-term volatility, while the opposite doesn't hold. Now that could be consistent with short-term investors who use the overall lower frequency volatility component as a signal for their trading decisions, hence causing higher frequency volatility, which means short-term volatility, to move based on revisions in lower frequency volatility. On the other hand, we think that long-term investors do not change portfolios due to short-term volatility revisions.